Good morning and welcome to the FAÇADE webinar series episode 8. Thank you for joining us for this sunny morning of July. And it's good to see that not everyone is on vacation. My name is Laetitia Marot. I am a Marie Skłodowska-Curie Fellow at the Innorenew Center of Excellence. And today we will talk about plasma application on wooden surface. I'm very pleased to welcome our speaker, Dr. Sebastian Dahle, who is a scientific associate and assistant professor at the University of Ljubljana in the Department of Wood Science and Technology. Dr. Dahle leads the Plasma Center at the Biotechnical Faculty, which was established in 2019. And his research activities include applications of non-thermal plasma for surface functionalization, enhanced coating performance, improvement of adhesion, multi-material composites, and plasma deposition. Dr. Dahle shows a particular interest in the use and improvement of bio-based materials and bio-based composites. Today, the presentation is recorded, and as usual, you can send your questions in the chat on the right of your screen. I will read them to Dr. Dahle at the end of his presentation. So now let's talk about non-thermal plasma technologies. Dr. Dahle, you can start.
Thank you so much for the kind welcome, and I'm very glad to be here. So, in order to speak with you about non-thermal plasmas and all the positive things that you can do with this, particularly in the context of facades and using bio-based materials. This is something that offers a lot of benefits that can be used, and this is something that we're gonna explore throughout the presentation. And that I feel is particularly worthwhile for materials with such harsh requirements, like with the weathering, the UV impact, the temperature differences over time, but also on different sides of the materials. So all these kind of impacts on the materials are things where plasma applications can definitely help you out to improve your products, or also to get good performances at maybe lower prices, at low production costs than this is currently the case. But before we look into the applications of the plasmas, let's first take a quick overview over the different kinds of plasma technology. And particularly, I will be focusing on atmospheric plasma technology and non-thermal plasmas. So in the very beginning, if we talk about the plasma, what is a plasma? What do we consider as this? And in general, a plasma is an ionized gas, meaning you're starting from a neutral gas, and by supply of energy, you ionize it. There's of course thermal plasmas, fourth state of matter, where you provide so much thermal energy that the gas starts to ionize by itself. But these are typically not well suited to use on bio-based materials or other sensitive materials because of their high temperatures. In contrast to this, the non-thermal plasmas are created using electrical energy, and this creates an ionized gas just as well, but without strong increase of the temperature of the gas. What you do get from the plasma, however, are different reactive species. So, for example, if you have a gas there where oxygen is present, you get a lot of different reactive oxygen species, including ozone, oxygen radicals, OH ions, hydroxyl ions, typically also other ions, and all these kind of different species can then foster chemical reactions that you can utilize for the different modifications of, in this case, surfaces. Speaking of this ionization of the air, that is provided by electrical energy, and the easiest way is to provide high enough voltages that the breakthrough happens, that the air starts to ionize. Now, we all know how this looks like if we just take the high voltage on two contacts and increase, if we just increase the voltage to a high enough level, what's happening is we're getting an arc, and so this is not really cold. A cold discharge is not really in a matter where we can use it suitably for any bio-based material, because it will just start to incinerate the material. And there's certain ways to avoid this. The first way to avoid this kind of arc formation in this hot state, like we see in the middle, one way to avoid this is just to limit the residence time. So to put this into a nozzle, to provide a high enough flow velocity of the working gas that we are using. And like this is the way to create a gliding arc jet. So this arc that's igniting is running down the electrodes, and the ionized gas with all those reactive species is like that advanced onto the surface. So these are typically local treatments, and in most cases require either a movement of the sample or a movement of the plasma device. But it's something that's relatively easily arranged and widespread available throughout all different industries. Different way to create this are so-called barrier discharges, where you simply place an isolator in between the contacts. The air will still ionize, but you won't get the formation of an arc, and so it's not gonna get hot. And this is something that's also very common for treatments of substrates. Like in this case, there's the wooden slide lying just on the table, and above the white tube, this is the isolator wherein the electrode is provided. So if we take a more in-depth look onto these, so this is a typical way on the right-hand side, how we can see this looks like with a wood sample that's treated. So this is an image provided by colleagues in Göttingen. And it's always essentially the same kind of setup. The electrodes are housed within an isolated like a ceramic piece, and the wooden sample is treated in between. One particular feature of these kind of plasmas you can see on the top image, which is that the plasma treatment affects the early wood and the late wood, if we're speaking about wooden materials, in different ways. And this is brought about mainly by the different conductivity and the different dielectric parameter of these parts of the wood. But it's also something that's quite typical for other materials. So if I have a heterogeneous material with different regions, it might well be that the plasma treatment affects different regions in different ways. So for this particular plasma, that's something just to keep in mind, because it's not the case for all plasmas, but for this kind of setup it is. Otherwise, this is one of the easier scalable setups. So you can over a larger surface simply increase the length of the electrode, or set up several of these electrodes in a row, and thereby relatively easily go to larger surfaces. However, the thickness of the sample is still limited by the voltage that we can provide. This is something that's very easily operated at atmospheric pressure in air, and we see the gas temperature is, for this kind of discharge, one of the lowest that we can get for the plasma treatments. So the temperature increase is typically lower than 10 degrees. Just for impression how this looks like in practice, so you can see on the bottom part of the video how the plasma ignites between the electrode and the substrates. Generally, I should note the videos that I'm showing are out of our lab, because this is easier accessible, and in many cases it's easier visible, and also more obvious for the technology than in many other cases. If we are looking at industrial equipment, most of the images are industrial equipment or taken from different kinds of publications, and so then in all the cases you'll find the sources linked in case you want to check back later. There's a different way to set this up that's then independent of the thickness of the sample, and these are so-called surface barrier discharges, where the plasma is ignited on top of a dielectric surface. So here's a schematic provided for this, where the electrodes are all embedded within an isolator, and the plasma ignites just on top of the plates. This can be in different kinds of shapes and forms. Here on the left-hand side, there's one example out of our lab. The point that's important to observe with these kind of discharges is that the plasma is not igniting in a large volume, but only really on top of the surface. So we need to come in relatively narrow for our substrates. So this works really well, very energy efficient at very low temperatures. It scales in 2 dimensions, so the scaling for large surfaces is very simple. This is independent of sample thickness. However thick your workpiece is that you want to treat, this will work, but only on relatively flat or evenly shaped surfaces. If there's a whole 3-dimensional structure, then it's difficult to properly apply this kind of a setup. Again, for the impression, so in the middle we see one electrode in our lab, and you see on both sides the plasma is igniting. It looks relatively static because this is igniting at a repetition frequency of some 10,000 times per second, 10 kilohertz. And so this is a live video of the discharge, how this looks in practice. Generally, for these kind of plasma discharges, I said they're very energy efficient. And the reason, just as one detail on the side, the reason for this is the gas phase chemistry. So we are exciting, particularly if we're using air as a process gas, very efficiently with the energy that you're providing. That's typically in this region around or slightly below 10 electron volts. We are very efficient to excite the nitrogen that's in the air, and this electronic excitation of nitrogen can then only be relieved again through interaction with other gas species. And in air, the main gas species where interactions happen is oxygen, where the resonant transfer leads to dissociation of the oxygen. And so this is what we're seeing in this case, that the O2 dissociation is very efficient, particularly still in this region where our plasmas are actually working. And so this provides a very high energy efficiency for what we're putting into the discharge. This is similar to corona discharges, and these I'm mentioning here now only on the side. These are relatively commonly used in the paper industry because this was one of the earliest available plasma technologies for surface treatments. The downside of this is that it's it's difficult to control the exact density and the direction of the discharge, and so homogeneity and scaling for the corona discharge is much more difficult to achieve than for the other kinds of plasma treatments that I'm presenting. So this is something that particularly for these kind of surface treatments of larger workpieces is less commonly used than the other ones. And then a very common thing that's often used are plasma jets. And we already saw one plasma jet before out of this gliding arc setup. In the middle, you're seeing one industrial setup that's using the very same principle, just in a more sophisticated way than we put it up ourselves in our lab. There's different ways how to set this up. So this can also be set up using a barrier discharge. We'll find a couple of different sources down below, and you can, if you're interested, go check back later for more details on this, or ask me and contact me about that. But suffice it to say that there's all sorts of different plasma jets for all sorts of different purposes, and so it's of course then important to select the right tool for the right job. Now, looking into the applications. Again, we're sticking mainly to atmospheric discharges, not going to look into vacuum and these more sophisticated setups like they're used in the electronics industries because of the simplicity and the lower costs to do this at atmospheric pressure. And particularly most of the applications that we are looking into are using air as a process gas. So there's no additional gas stream, no additional gas required for these kind of plasma treatments. And already with the simple setup in air, what you're receiving, what you're yielding from the plasma treatment is actually effects on all sorts of different levels. So in this case, we're looking particularly on wood, but the same holds true for all sorts of other bio-based materials. And particularly the molecular effects are the very same also on all sorts of polymeric, metallic, and ceramic materials. So one thing that you of course see is macroscopically that there's an activation of the surface, that you change the components of the surface free energy. In air particularly, what you'll typically get is a hydrophilization, a better spreading of water. What you're also typically getting is a better penetration of different liquids that's in most cases including both water and non-polar liquids, both polar and non-polar liquids. But also liquid spreading, generally wettability. So all these kind of macroscopic effects, and then the further resulting adhesion strength if I'm combining this with a coating or with any kind of glue. These are typical things that are looked at. Microscopically, we'll often find etching, smoothing the surfaces. We're finding better contact areas with other substances with additional steps that follow after the plasma treatment, like coating or gluing. One thing that we're noticing is the removal of grease, for wood, the removal of extractives, and particularly if we are speaking about fibrous materials, then also plasmas can be used to change the topochemistry of the fibers. On the molecular level, we find functionalization that's generating all sorts of different reactive groups. And so an advantage of the plasma treatments typically is you have inside the plasma all sorts of different reactive species. It provides means for all sorts of different reactive reaction pathways. So there's a lot of things that can be generated by the plasma, and a lot of reactions that can take place, but also at the same time they will take place. And it's to really specify one reaction that you want to have as the main part of the treatment. That's hard to really constrict. So you're typically getting, for example, for air plasmas on wood and on many polymer materials, you're getting oxides, hydroxides, carboxy groups, even ether and peroxide groups, and this can then also help to create radicals or to induce grafting. Also, depolymerization can be a topic, an issue, or a benefit on different polymeric materials. Again, speaking about wood and speaking about other bio-based materials, main components for many of these, of course, are lignin, cellulose, hemi and holocellulose. And generally speaking, you'll find an oxidation in all of these materials, much less so on the cellulose than on particularly the lignin. The lignin is most quickly reacting, and particularly with all the benzene groups that's included. So these are the most reactive to the species coming in from the plasma. So this is also something to keep in mind, how this is affecting different parts of your composition of the workpiece. And looking for the effects, there's all sorts of benefits that we can create from this. One for the very beginning to look into is reduced sensitivity to water, reduced sensitivity to moisture in general. In this case, we plasma treated with the industrial plasma jet, with the gliding arc jet, like we saw in the pictures before. Different wood-based materials. We had MDF, solid beech, and spruce. We had also OSB. And what we found in general is that for different kinds of plasma treatments, we find a reduction of the water uptake through a water-based stain. So we had a plasma treatment, water-based stain was applied. Samples were afterwards immersed after the stain dried and cured. Samples were immersed in water for 3 days. And we do find on samples like OSB with those larger defects and with generally less well spreading and less well covering of the stains, and minor impact, but we found really a major reduction for the water uptake on spruce, still a significant one on beech, and also a notable one on the MDF material. So resistivity to moisture and water is definitely something that can be improved, and that then also will increase the lifetime of any object that I will produce out of this, or where this is going to be used in the production. Color stability can be improved, but this is not the case for all different materials. So in the case of spruce, we found that color changes after weathering of a sample, spruce sample that was plasma treated and then coated with the stain, is less pronounced than for one that's not plasma treated before coating with the stain. But these effects are rather minor and are not the main benefits of the plasma treatment. Much better benefit is a reduction of cracking, and as a consequence of this, then less infections with different biotic factors. So on the left-hand side, you'll find a sample before and after weathering with typical infections. This is a sample after 10 months of aging, where on different spots on the sample, cracks did appear as evaluated, and also we see the shading by the biotic factors. And in the evaluation in the tables, we'll find that this is much less the case for different kinds of coatings. So using tung oil, water-based stain, also a solvent-based UV protective stain. In all these cases, both cracking and the infections were reduced by the plasma treatment during the following 10-month weathering period. Mechanical stability can improve for composite materials. So this is an example from the literature where they produced plywood, and for different materials used, using just the reference. In the left case, I believe it was spruce, if I remember all right. In the one case, non-treated, unmodified. In one case, the thermally modified wood samples. And we find that in most cases where plasmas are used, the mechanical, the shear strength for the samples are improved. We also see, however, that in most cases, the variation between individual individual specimens is increased in contrast to the reference sample that was not plasma treated. Not in all cases. In some cases they were reduced, but this is something that can occur, that plasma treatments provide benefits, but provide a larger spreading of the actual values than we had before. Some cases reduces, in some cases it improves, it increases. We also see for different wood species that plasma pre-treatment and then afterwards gluing with melamine increases not only the shear strength of the bond, but also enhances the curing times, so shortens the curing times. Not in all cases, but in some cases this was notable, as published in the paper. So this is something that can be used, but as I think is obvious from this overview and also from the previous slides, this is really something that differs from different materials used. So in this case, already just different wood species. So the same is true for different bio-based materials. The same is also true for other materials. So even if I have the same base polymer, the residual additives or the residual monomer content within the specimen can make a difference for the absolute effect of the plasma treatment. And so between different batches, there might be some variation even for the polymers that are quite well controlled. One thing that is particularly interesting with plasma treatments is the combination of different materials classes. That's usually quite challenging. And so in this case, what was done is pre-treatment of different substrate materials, as seen on the top left side. And afterwards, these adhesion strength tests of the formed lap joint were undertaken. We see for the plasma treatment that in some cases there's an impact on the roughness. So for example, on steel substrates, the roughness was slightly increased. On aluminum and wood, there's no major difference on the micrometer roughness, as you can evaluate in the microscopes. However, in all cases, the surface free energy, both the polar and the non-polar components were significantly modified. And for different glue systems, so we have used epoxy, polyurethane, polyvinyl acetate, and melamine urea formaldehyde. For these different glue systems, there's a different impact. Particularly on wood, there's a minor increase for the typical wood glues, a minor decrease even for the less typical epoxy and PU glues. So for wood joints, using these kind of adhesive systems, the plasma treatment would not be advisable. However, for the combination of different materials classes, we see a particularly increase in all the cases. And one very notable one is on the aluminum substrate. So we find that not only, with the exception of the melamine urea formaldehyde, are all other three adhesive systems perform better than the best non-plasma treated sample did. But also what we find is that even the relatively simple water dispersion based PVAC adhesive performed better than the usually utilized for this application epoxy adhesive system. And so this kind of improvement for the PVAC, this is something particularly interesting to look at in the future. But as you can see, this is something even on the steel, we find that the PVAC glue after plasma treatment performed equally well to the epoxy glue without the plasma treatment. So this is something where directly both an environmental and an economic impact will benefit from the plasma treatment. As a last topic, just to briefly go over, is plasma deposition. So in this case, more complex working gases are used. So typically, there's precursors utilized that are added to the working gas. These can be silicones, like disiloxane or others. These can be fluorocarbons. These can be simple hydrocarbons, depending on what kind of material you want to deposit on the surface. And the typical procedure is that this is mixed into the working gas either before feeding into the plasma or in the afterglow of the plasma. So in particularly if you're using a plasma jet, then in the lower part only after the plasma is already ignited. This can be done using nebulizers, gas washing bottles, or all these kind of things. So there's all sorts of solutions that already is available and already is also used industrially. One particular example on the right-hand side, so this is a small system that we have in the lab with a mobile digestorium to protect from any aerosols that come out of these plasma treatments due to the conversion of the precursors. And this can be used in such a way that it's either producing from silicone-based precursors to either produce hydrophilic or hydrophobic surfaces. So on the top side, we see the contact angle measurement for a hydrophilic sample. When the drop is lowering, you will see directly upon impact, it's spreading across the surface and even spreading within a single frame, so that there's barely the possibility to even measure the actual contact angles. So this is one sample that definitely falls into the superhydrophilic category, whereas for different examples, we find the cases where the droplet is contacting the surface, but it's repelled so much that it's rather sticking to the tip of the contact angle measurement device. And contact angles here that were measured are strongly beyond 90 degrees, typically around, let's say, 130 degrees. So this is considered a superhydrophobic sample, and both of these stem from the similar precursors and can be arranged just by adjusting the plasma treatment. So these are, again, also things that are available on an industrial scale and with those equipment. So with this relatively quick overview, all these are, I believe, applications that do make a difference for facade materials. If we're speaking about composite materials, speaking about their mechanical stability, their resistivity to moisture and water, speaking about their resistivity to UV and light, also for combining different materials and improving these joints, while at the same time also improving the economic, the environmental impact of the production method. And so there's a lot of things that can easily be utilized and where plasma is bringing many benefits. But as we also saw, there's often quite a strong variation between different wood species or different materials, also variation between different applications. And in all cases, of course, economic feasibility needs to be compared to conventional techniques. Very often, plasma is significantly cheaper than a comparable conventional technique, but not in every single case. And so this is obviously always a case-by-case decision, and the case-by-case optimization is needed. Anyway, in conclusion, I believe with this brief overview, I was able to show you that plasmas are actually something that's well established industrially. They are scalable, and they do offer various opportunities for wood technology, for wood protection, and also for use with different other bio-based materials, and particularly in facade applications. If a case-by-case approach is actually taken and things are optimized like that. And with these words, I like to thank you for your attention. I'm open to your questions, and I'm eager to answer all of these. I hope for a lively discussion, and if there's any details out of the presentation that you would like to check back later on, you'll find the link on the left-hand side, both as a DOI and as a QR code. So you can get the presentation with all the different materials, all the different site literature, so that you will be able to see and take a detailed look yourself. Of course, also, you're welcome to always contact me and get in the discussion later on. But for now, yeah, I'm looking forward to your questions here in the webinar.
Thank you very much. It was very, very interesting and clear presentation. So please, if you have questions, type them. Yeah, so we have one question from Vera Pandian. Nice presentation, thank you. Do you change the energy of the plasma source? How to optimize the energy of plasma for a certain wood species? After the plasma process, are the radicals like peroxides free or radicals formed on the wood surface? And do you check them?
So immediately a couple of questions, and I try to answer separately. So changing the energy of the plasmic source, there's different ways to change the power that's supplied into the plasma, and there's different ways to change a distribution of different reactor species. But both of this depends on what kind of plasma you're using, what type of plasma. So we saw in the beginning, there's for example, gliding arc jets, dielectric barrel discharge plasmas of different varieties. And so these can be influenced in different ways. But generally, the waveform of the high voltage you provide, how is this shaped? Are these short pulses? Or is it more like a sinusoidal form? This makes a huge difference, both for the energy efficiency, but also for the processes coming out. And so this is something to weigh against each other. There's typically a way to change the power input rather than the peak voltage of the high voltage provided to ignite the plasma. So this is typically the way that you can change there. So yes, there are ways to change the energy and to optimize this. How to do this? Well, like I said, this is a case-by-case thing, depending on the equipment you have. There's different means, and the manufacturer or the one who did the base study more maybe for this can provide you with more information for this particular kind of equipment, how to do this there. How to optimize this then is the second point. Well, you want to optimize this for a certain kind of performance. So a very simple, very quick way to do this is to look at the contact angles or the surface free energy, because this is an integrating way of measuring what's going on the surface. And particularly the water contact angles in many cases are very indicative of a performance later on regarding gluing, painting, or all sorts of other applications. So main indicator that's used by most people are water contact angles, but always the best way is to optimize really for the parameter of performance that you do want to actually improve. So yeah, for a longer answer, but this is typically how you would perform this. After the plasma process, what's really there on the surface? So there's several publications reporting that radicals are formed on the surface, but particularly radicals, this is something more difficult to really detect. And so this is in most publications not specifically investigated, particularly regarding the radicals. There's, like I said, all sorts of different species that are formed. Radicals probably are a minor fraction, the much more common thing that's formed on particularly polymeric or bio-based materials, so organic substances. Typically what's formed are exactly these hydroxide groups, carbonyl groups, carboxyl groups. These are the most common things that for the most part form. Free oxygen radicals on the wood surface is the same as for radicals on as terminal groups on the polymer or on the organic material. It's expected that there are some residence time, but the amount of these is not really well investigated in the literature. So this is something to that's very interesting to further investigate in the future, how much really radicals are present and which kind of radicals or to which fractions these are. But hard to access, and so this is still an open question that needs more investigations. So with this one, not as pointy an answer, but hopefully still yeah, satisfactory as much as possible from the current state of knowledge.
Okay, thank you for covering the several questions. I had also one question, maybe you already mentioned it. You said that the plasma can change the mechanical properties of the material. I was wondering how deep it penetrates below the surface in the material.
So there's several different things going on in different depths of the sample. One thing is the very outermost sample, those parts that are directly exposed to the plasma. There you find the most chemical changes on a depth of maybe some 10, 15, 20 nanometers. So the most strong change to the surface is really very restricted. If there's etching going on, then still it applies from what's left as a surface. The most chemical changes are on the outermost surface like that. There's influences reported up to some 20 to 50 micrometers deep, but those are less pronounced. And this is something that's very obvious if you compare different studies and different results. If people investigate, if researchers investigate the result of the plasma using infrared spectroscopy, this is something that's typically having an information depth of a couple of micrometers, and there the changes are really minor. There are really some details where people are looking, but it's not like a major change is visible there. Most of the chemical changes are investigated using methods like X-ray photoelectron spectroscopy or these kind of methods because they're so surface sensitive. This also means this is something that's really nice to improve an interface, for example, for gluing or coating. Just a pure modification by the plasma functionalization by itself is in most cases not a good determination of the surface. It's a different story if you do plasma deposition, you're depositing material on top of this, but just as a functionalization, since the main part of the modification is on the outermost few 10, maybe nanometers, this is something that's relatively easily then also mechanically impacted over time. And so typically really rather an intermediate step as a pre-treatment than a final treatment. For final treatment, it's really rather the plasma deposition. However, there is some changes that are also affecting the wood if we're speaking particularly about wood in higher depth. So for the wood and also for some other bio-based materials that contain bound water, free water and bound water, what we find is that this moisture content is changing by the plasma treatment. Plasma treatment leads to an enhanced drying in the surface near region, let's say a few millimeters near the surface for sure. And this is something that's obvious even after relatively short treatment times. By that, it's also changing, of course, other physical properties of the wood, dielectric parameters, conductivities, if these are important. This probably is part of how the penetration of different liquids is improved. And as said, this is affecting not only penetration of water, but in most cases also strongly affecting penetration, or in many cases affecting penetration of non-polar liquids. And so that there is effects that are going on in higher depth than what we can see for the chemical modification. These are not 100% clear really how much is going on there. No, let's rather say how deep is this going on and how strongly is this impacting other parameters. It doesn't seem like this has a major impact on mechanical properties. There's nothing observed like this, but for sure this is something that's interesting also for other kinds of application and for further processing steps of any workpiece. And so this is still ongoing research. This is not so much the case if you have polymer examples or generally other kinds of materials classes, metals, ceramics, polymers typically are are only affected more or less on the surface, and there's not so much of a microstructure porosity, and these kind of things that would need to be taken into account.
Okay, thank you. Very clear explanations. Thank you again for your presentation, for answering the questions. Thank you to all the participants for joining us today. And I hope you enjoyed the webinar, and I hope you will come back again in the future to see the next webinars. So I wish you a very nice day and take care.
Thank you very much, and see you.
Bye.
Bye-bye.
Bye.